My name is Om Nalamasu. I'm the Chief Technology Officer of Applied Materials, and I'm also the President of Applied Ventures, the venture arm of Applied Materials. Materials engineering is the ability to control thin films with atomic precision on an industrial scale. Materials innovations, along with the dimensional scaling, have been the foundational elements of unprecedented productivity gains with semiconductor industry with the Moore's law. This is what makes it possible for you to have a supercomputer in your pocket and have it last all day on a single charge. Semiconductors are playing an increasingly critical role in the global economy, touching everything from automotive to agriculture to security and global climate change. With the pandemic, there is a new recognition that industrial leadership and economic prosperity are now intimately connected to leadership in information and communication technologies, along with resilient semiconductor supply chains. The need for a coherent global approach to the semiconductor innovation infrastructure that enables continued advances is now. Let me describe a few of the challenges we face as an industry and why I'm particularly excited about the limitless opportunities ahead of us. First, the two-dimensional scaling of Moore's law has slowed down. The need for improved power, performance, cost, and time to market, however, continue. The solution is to create these tiny nanometer structures in 3 dimensions, whether it is for memory or for processors. Think of this as building skyscrapers in Manhattan versus suburban sprawl. This is only possible by creating and controlling the materials and interfaces of these structures at an atomic level and on an industrial scale. We call this materials engineering. Second, with the world's insatiable appetite for electronics powering everything from data centers to toasters, we must be vigilant about the impact that these devices can have on global energy consumption and climate change. Energy consumption for general purpose computing is growing exponentially, doubling every 3 years. But the world's energy production is growing linearly at only 2% per year. According to SRC, in about 20 years, the needs of general purpose computing alone are going to outstrip the projected global power generation. Materials engineering again shows a path to heading off this scenario. New materials, 3D structures for DRAM and NAND memory, logic, and new device architectures all show promise for energy efficient computing. I'm particularly excited about technologies that enable what the industry calls advanced packaging or heterogeneous integration. That is, putting different special purpose chips called chiplets closer and closer together so that they consume less power and improve performance. Third, while the challenges and opportunities within the semiconductor ecosystem center around materials engineering are the most exciting, I also firmly believe that there are other global inflections that can be enabled with materials engineering. Let me give you one example. Energy storage. Improving the energy density of the batteries simultaneous with reducing cost per kilowatt hour for electric vehicles can dramatically improve adoption of electric vehicles, especially as they approach cost parity with the internal combustion engine. These energy density improvements plus fast charge are enabled through the use of silicon and lithium anodes with materials engineering technologies. There are many more areas where materials engineering can enable global inflections, more than I have time for today, but I would be happy to follow up if there is interest. In summary, while there are limitless opportunities for innovation with materials engineering for semiconductor industry, you can see that these big problems are quite complex and cannot be solved by one company or, for that matter, by one country alone. It requires collaboration across borders based on the rule of law and respect for IP. National support for a pre-competitive coalition of global semiconductor companies, institutions, such as imagined by the CHIPS Act, is an essential element in this effort. In closing, I am most excited about the energy efficient computing driven by materials engineering in building a more abundant and sustainable world. Thank you.